Okay, so this problem, I have a mass that is being held under some water by a spring, and the spring is stretching, and we're trying to figure out how much the spring is stretching from here to here, right? So this is like if you've ever been in a pool and you push a ball or something under the water and then it shoots back up, right? This thing is less dense than the water, and so it's trying to shoot out of the water, right? And it's being held back by a spring, and we're trying to figure that out, right? So really, we're just trying to figure out the buoyant force. If we could get the buoyant force, we could solve. Okay, so let's write stuff we know. I know buoyant force is rho vg, the density of the water times the volume displaced, right, times g. And I know for a spring force is the spring constant times the stretch of the spring. Okay, so let's do free body diagram. So this block right here, there's gravity pulling down, and then there's also this spring pulling back, right? The force of the spring is pulling downwards. It's not pushing it up. The force of the spring is holding it back. And this buoyant force is pushing up hard, right? Trying to make this thing go out, but they're all balanced, right? Because that spring, the mass is not accelerating. So from this diagram, I can write an equation, right? I can say that my net force is 0, and that's Fg plus the spring minus the buoyant force. So if I want to solve for the spring, because that's the point, I need the spring to get the stretch, right? Let's rearrange this and solve for the spring. So I know the force from the spring is equal to, if I move this over, well, I'm going to keep Fs by itself. So I'm going to subtract Fg and I'm going to add Fb. So that's buoyant force. I add this to the other side, and then I subtract the weight. So the spring force is the buoyant force minus Fg. Okay, so let's plug in what we know. Spring is K times delta x, but the delta x I'm finding is delta L, so delta L is the delta x in the equation. Right, so this is going in for that. So K times delta L equals the density of the water times the volume of the block times G minus the mass of the block times G. Okay, I don't have the mass of the block. But, actually I do. I have the block of wood. What I don't have is the volume of the block. But I know that density is equal to mass divided by volume, right? So if I took the density of the block, that's the mass of the block divided by the volume of the block. So that means the volume of the block, if I rearrange this, equals mass of the block over density of the block, right? And I can take this and put that in for V. So now I have spring constant times delta L, which is what I'm trying to figure out, equals the density of the water times the, what I got here, mass of the block over density of the block, right, times G, minus the mass of the block times G, right? And so I have this equation. I can take this equation and I can solve for delta L. I should know everything. Density of water, right? Just, that's one of those things off the top of your head. Density of water is always 1,000 kilograms per cubic meter, right? Water is one of those easy ones. Mass of the block, I have it. Density of the block, I have it. G is obviously 9.8. Mass of the block, I have it. G is 9.8. K is the spring constant, right? Got the spring constant. I can solve everything else. Not hard, right? But it starts again, like everything else, drawing a free body diagram.